Welcome to Chemistry Lover, and today in this video I am going to discuss about a very interesting topic, and that is the Vinylogous Felkin-Anh model. Now you may not be familiar with this particular model, but you are familiar with the Felkin-Anh model, right? And if you don't know about Felkin-Anh model, you can watch my video on that. I have several videos in my channel on this Felkin-Anh model. So first you have to learn about the Felkin-Anh model, and then only you can understand this topic. So I have written down two examples, this one, and both of these molecules you can see there is a vinyl group. So this is the vinyl group. Why it is vinyl? Because it is vinyl with respect to this carbonyl group. In case of normal Felkin-Anh model, what we do, we look at the stereochemistry of carbonyl addition, and that carbonyl group is actually adjacent to a diastereotopic center or a chiral center, and in this case this is a chiral center, but it is not directly attached to the carbonyl group, rather it is separated by this alkene. So that's why it is called vinylogous position. Now the interesting outcome of this reaction is, you can see in both cases the chiral center has the same configuration here and here, but the only difference is the stereochemistry of the double bond. In the first one it is trans, and in the second one it is cis. And for that, in the first case, when you add Bu to CuLi, that is the Gilman's reagent, in presence of BF3, you get a product where the incoming butyl group and the existing methyl group, they are trans to one another or anti to one another, whereas when the stereochemistry of the double bond is cis, we can see the existing methyl group and the butyl group, they are seen to one another. Now how this stereochemistry comes, that we can explain by considering the Vinylogous Felkin-Anh model. So what we do in Felkin-Anh model is, first we draw the molecule in the Newman projection formula, and here we will do the same. So this is the Newman projection formula. So first we will draw it for the trans one. So if we have to make the stereochemistry trans, we have to put this ester group here. Okay, so this is our ester group and the hydrogen will be inside. So this is trans, so that's why it is away from the other part. Now you can see how we have to place the other group. So before that we have to draw this stereo center or this chiral center in proper way. So this chiral center actually look like, so here you have the phenyl and the methyl is actually above the plane, and the hydrogen, which is not written for clarity, it is actually below the plane, and this is our other part. Okay, so to draw it in the Newman projection formula, what we will do, we will put the phenyl group at the top, and now you can see here we have the methyl group and here we have the hydrogen. Now this is the case, this is one of the many possible conformations, but in this particular conformation you can see both this side and this side, they are blocked by, in this side it is blocked by this phenyl group and in this side by this methyl group, so nucleophile cannot approach. So what we have to do, we have to rotate it in order to show the nucleophile a proper path so that it can attack. So what we will do, we will rotate the structure, but this part remains same. So here we have this, and here we have this hydrogen, here we have another hydrogen. Now we will rotate the sigma bond. So if we rotate, the phenyl will come below and the hydrogen will go here and the methyl will come here. Now you can see, although this is slightly more higher in energy compared to the previous one, because you can see here we will have this 1,3 allylic interaction between this hydrogen and this methyl group, which was not there in the previous structure because there was no such group. So this is slightly higher in energy, but at the same time now the nucleophile, in this case the Bu minus, which is attached to, of course, to the copper, now the nucleophile can easily attack over here. Why? Because here we have only small hydrogen atom. So if this attack takes place, and this is exactly same as the Felkin-Anh model, right? So now if it attacks over here, what we will get? We will get So yeah, just let me erase it down. Yeah, so first we will draw the other side. So this is the backbone, this one hydrogen, this phenyl, and we have this methyl over here. So now you can see this is the attack of the butyl group. Here we have the hydrogen and here we have the CO2 group. This is the product. So this is the product we will get out of this reaction, okay, and it is for the trans one. Now you can see in this particular case this hydrogen and this hydrogen, they are they are goes to one another, butyl and methyl, they are goes to one another, and this group they are goes to one another. And in the product also you can see, in the product you can see so actually it is a erythroisomer. So it is erythroisomer, and if we look at the product, so this is our product, you can see this is our product. So in the product you can see this phenyl and this large group, this is anti to one another, this methyl and this butyl group, they are anti to one another, and also the hydrogen and the another hydrogen, they are also anti to one another. So this is also a erythroisomer, erythro. So this is erythro, this is also erythro. So actually if you convert this structure to this flying wedge formula, you will get the same thing. So this is how we get the first product. Now let us look at the second case when we have the cis stereoisomer, okay. So again we have to draw the Felkin-Anh model, and in this case the ester group will be inside because it is cis, and here we have the hydrogen, here we have the phenyl, here we have hydrogen, and here we have methyl. And actually in the previous case it follows the Felkin-Anh model, which I forgot to mention. And now here we have another hydrogen. Now again you can see the in this particular conformation the nucleophile can attack from this side, right, which is possible, but this conformation is very high in energy. Why? Because in the previous case you can see there was, so in the previous case what we can see is we had only a small hydrogen atom and methyl group, and the allylic 1,3 allylic strain was not that much high. But in this case you can see you have methyl group, and this is a very large group, COO2ET, this is a very large group. So there will be a high amount of 1,3 allylic strain which will not allow this conformation to exist. So the population of this particular conformation will be very low, and it cannot react through this conformation. So it will rotate, and it will go to the previous form. What is the previous form? The previous form is actually, you can see this, you have this hydrogen, you have another hydrogen over here. So if this rotates, the phenyl will go above, here we have the methyl, here we have the hydrogen. Now we can see the attack of the nucleophile from this side is very unfavorable because of the large methyl group, but some nucleophile can attack from this side, although it is not possible according to the Felkin-Anh model. Actually it is not like it is not possible, it is not favorable. So it is less favorable according to the Felkin-Anh model, but in this case the other conformation has so high allylic 1,3 interaction that this attack from the medium size group, this methyl is actually here the medium size group. So attack from the medium size group, which is not favorable in case of normal Felkin-Anh model, but now it becomes favorable because of this 1,3 diaxial interaction. So now if this attack take place, what we will get? We will get this product. So phenyl, here we have methyl, here we have hydrogen, and here we have this so we have hydrogen, we have this butyl group, and we have this large CO2 group. So now you can see this phenyl and this butyl, these groups are anti to one another. This hydrogen and this hydrogen are anti to one another, but this methyl and these are anti to one another. But we have to find the relation between this phenyl and this large group. So you can see in this particular structure, this hydrogen and this hydrogen, they are anti, but this either of these two pair, so this pair, this phenyl and this large group, they are syn or gauche, they are gauche, and this methyl and this butyl, they are also gauche. Okay, but so this is a trio isomer, and our product for the cis one, you can see this is our product of the cis isomer. Here also so we have to put the hydrogen group, we have to put the hydrogen group. So if we put the hydrogen group, it is like here we have the hydrogen which is below the plane, and here we have the hydrogen which is below the plane. So you can see this hydrogen and this hydrogen, they are goes to one another, but this phenyl and this is also anti to one another, and this methyl and this butyl, they are goes to one another. So this is also a trio isomer. So these two are actually same. So if you convert from this Newman projection formula to this flying wedge projection formula, we will get the same thing. So we can see how we get different products. So the interesting part is in the cis isomer, for this cis isomer, the Felkin-Anh model is not obeyed, so it is actually the anti-Felkin-Anh product. So for the trans isomer, we get the Felkin-Anh product, but for the cis isomer we get the anti-Felkin-Anh product, and in this case this is the major product which has almost 70% of the total population, and here also it is the major which has 70%. So the major product of the trans isomer comes from the Felkin-Anh model, whereas the major product of the cis isomer comes from the anti-Felkin-Anh model. So this is very interesting. Now this effect of the modified, so this is actually called the modified Felkin-Anh model, and this modified Felkin-Anh model is not so straightforward. In some cases we get the stereochemistry totally different. For example, let us write another example. So let's say you have this thing, we have this CO2 ET over here, and here we have this trans geometry. Here you have methyl, but now the group is different. Previously we had phenyl, now we have this silyl, some silyl group. Okay, so here if you add, let's say, Me2Culi, what we will get? So according to our previous discussion, we should get this product. So we have this OSIR, this methyl above the plane. So because it is trans, so we should expect we will get the addition of the methyl like this. So this methyl and another methyl which is incoming methyl, we should expect it to be trans to one another or anti to one another, but this is not the product. In this case the product is totally different, and we get a product like this SIR. We have methyl over here, but now this is also seen, this is also above the plane, and what we get, this methyl group and this methyl group, they are seen to one another. And interestingly, when we have the, let's say when we have the cis isomer, this one OSIR, and here methyl, interestingly when we have the cis isomer, we get the other one. So this CO2 ET, we have this OSIR, we have this methyl, and now we get this methyl below the plane, right? So this is very interesting. Whatever we discussed in the previous problem, we get the totally reverse outcome in this particular case. So I will not discuss the explanation in this video. In the next video I will discuss it. If you can explain it or if you can answer it, please let me know in the comment section, and I will let you know what is the explanation in the next video. So I hope that you understood the concept. Thank you for watching.